Okay. So I'm talk about the zip code of quarks, leptons, and Higgs bosons, and this is just a question that when we discuss string theories or theories in extra dimensions, a lot of the properties of the theory are determined by the location of the fields in extra dimensions, and I will actually show you in some way that this is very important. In fact, this is something which I want to do in the top-down approach. Now, I had two previous speakers here which are strongly insisting on a bottom-up approach, but essentially what they were doing was we learned when we studied with the heterotic string theory. And so it was, you see, this discussion about how the mu problem can be solved, we in a certain way found experimentally. Some things we put in, we wanted 3 families, but 3 families or 4 families, 5 families doesn't tell us so much about the structure of the theory, except for the fact that we have those. When we constructed these models, we actually found out that there are certain general properties which in some way turn out to happen, like for example that the Higgs concerning Higgs bosons and also to the top quark. And in fact, it turns out that what we learned that in all the successful models, Higgs bosons and the top quark had to live in the bulk, had to live in full 10 dimensions, whereas other families could be localized, exhibiting family symmetries and have a smaller Yukawa couplings than the ones which live in the bulk. What we also learned is that we got a special scheme for supersymmetry breakdown in this theory, which we get in general also in the type 2 theory, and that is what is known as the mirage scheme. Now all these things in some way are remnants of some n equal to 4 supersymmetry in higher dimensions. For example, if you start with a 10-dimensional theory and you compactify it on a torus, an n equal to 1 and d equal to 10, you in fact get down to an n equal to 4 theory in 4 dimensions. So you have n equal to 4 supersymmetry. That's of course not the exact supersymmetry, but it's a symmetry at the tree level for the fields in the untwisted sector or the bulk. So in that sense, there is more supersymmetry there, and that plays a role for certain things. And these are the things which I want to explain. I will talk about 2 things. One of them runs under the name of natural SUSY. That is partially coinciding with other people called natural SUSY. And then there's something which comes at the end, which I'll call remote SUSY. Okay, so the geography of fields in extra dimensions is important, that we will see. We have to look at the location of the quarks and leptons, and also the relative location of the Higgs boson. So for example, if a particle is close to the Higgs boson, typically you would expect it to have a larger Yukawa coupling than otherwise. But we will also see that in this picture there is a localization of gauge fields. So at certain points in the extra dimensions you have different gauge groups. You have, for example, seen that in Stewart's argument when he showed you the SU6 at some points and at others. The 4-dimensional gauge group, of course, we will consider to be SU3 cross SU2 cross U1. This is just one group which we have there, and it's the common gauge group of subgroup of all these places, groups in the various dimensions, which could be much bigger. So you could have a 4-dimensional SU3 cross SU2 cross U1 gauge theory, but you could have certain points in space where the actual gauge group is SO10. So now, of course, we have to compactify, and the nice picture is that you compactify it on the Calabi-Yau manifold, and then you have to ask the question, where actually do these fields live? So there are cycles, some fields can wrap around cycles, cycles can shrink to 0, cycles can be big. In any case, whatever you do, you have to make an approximation, and the approximation which we are doing is that we replace this beautiful object by something which looks pretty simple and trivial, which is an orbifold. Now the good thing is that on the orbifold you can actually compute. It's an approximation where you can compute, and it's actually an approximation which captures a lot of the knowledge which you want to have in a simple model. It also means that in such a model you have enhanced symmetry groups which are much bigger symmetries at certain points or at certain locations than you would expect generically in the whole space when you look back at this Calabi-Yau space. So now let's look at this orbifold picture of the heterotic string. We have the following situation. We can have fields that live in the bulk, so they live in the full 10 dimensions. This is the so-called untwisted sector. And then we have twisted sector. We can have fixed points and fixed tori. So fixed points will be points in extra dimensions, and fixed tori will be tori in extra dimensions. So they either live in 4 or in 6 space-time dimensions. As I said, there will also be a localization. It's actually not a localization of the gauge fields as such, but it shows you just that at certain points you have more gauge symmetries than you have generically in the 4-dimensional world. So for example, this is an example of a theory which has the gauge group SU3 cross SU2 cross U1. Nonetheless, if you are, for example, sitting at this, I don't matter. If you're sitting, for example, at this SO10 point, and you know that there is a field, the electron is sitting at the SO10 point, actually it turns out that the full first family has to sit there, because there they come in full representation of SO10. In other places they are different, and of course it's clear that the Higgs, where you want to do doublet-triplet splitting, should not sit at such a point of enhanced symmetry. So in fact these are the symmetries which lead you to the standard model symmetries. Now we had taken a specific example, which was the set 6-2 orbifold, where we actually tried to let go through and say, can we construct reasonable models? With the spectrum of the MSSM, the exact spectrum with family symmetries, Yukawa unification, a large top quark Yukawa coupling, can we find models with R parity, solution to the mu problem, and also can we discuss something about supersymmetry breaking via gaugino condensation? What is the hidden sector gauge group if you do these kind of things? So this led us to a few hundred models, and from these few hundred models actually we can learn a few things, and that's what I want to discuss in the following. Let me first discuss again the sectors, how they look in the set 6-2. So the set 6 means there is a rotation by 60 degrees underlying, so this we call theta. We have the untwisted sector, which is in the bulk. Then we have the theta sector, and the theta sector consists of fixed points. So we have here 12 fixed points, and fields can sit on these fixed points. That's the general thing which we can do. There's a theta squared sector, and the theta squared sector has fixed tori. So it's here that we have 2 times 3 fixed tori. The 2 fixed points 3, 5 in the first one become identified by a 60-degree rotation. This is why this counts only as 1 fixed point. So these are fixed tori. And then the theta cube sector also has fixed tori, but here the second torus, the second compact complex dimension is represented by a torus. So now we have to ask the question, in these models which are successful, which give us the standard model, where actually do we find quarks, leptons, and Higgs bosons? This is a benchmark model which I just want to explain the structure. So if you are at the orbifold fixed point, we have an enhanced symmetry, and with that enhanced symmetry we have additional U1s, but we also have vector-like exotics. And now the question is, can we, but we also have an anomalous U1 which drives a Fayet-Illouz term, which in fact drive certain field getting a non-vanishing vacuum expectation value, and you can now ask the question, do I have D and F flat directions, which allows me to break all the symmetries and which remove all the exotics. And in fact, this can be done, and here in the remaining group here would be SU3 cross SU2 cross U1 times an SU4 hidden. So the SU4 hidden will be later used for gaugino condensation. So this, for example, is a spectrum of the model where we actually show all the fields, and we also in some way keep the broken B minus L charge, because that is useful to discuss questions like neutrino Majorana masses and all these kind of things. But I will not discuss that here in detail. I will first look at the location of the Higgs boson. So typically there could be a multiplet of Higgs doublets and triplets in the splitting. And in fact, when we start with this theory, before we do the blow up, or before we discuss this breakdown of the additional U1s, we typically have a lot of doublet pairs and a lot of triplet pairs. Of course, at the end, the triplets should be heavy projected out. That's usually not a big problem to do, but exactly 2 Higgs doublets should remain light. Now, very often, in general, so if you go at the generic case, you have 24 Higgs doublet pairs, and you say, I want to make 23 of them heavy. And you can do it. But then you have to ask the question, why didn't I try to get the 24th pair heavy as well? And that's essentially the mu problem. And in fact, what happens in our cases is that in these models, like the benchmark models and many models in the mini landscape, we found that exactly 1 Higgs pair remained light. We were very surprised about that. And in fact, now we in some way understand that it's protected by a discrete symmetry. We found that also in this one, and you have heard Michael's talk just before, that he in a certain way is now constructing models which use this information from the bottom-up point approach. The reason why this happens in these models here is that the Higgs bosons actually live in the untwisted sector. So Higgs bosons are not localized. So the zip code of the Higgs bosons is that you essentially do not know where they are. You know they are somewhat in extra dimensions, but they are delocalized. And you see these are fields which you would have gotten already when you do just the torus compactification. So this also means that these fields, they were gauge fields in higher dimensions. So this is gauge Higgs unification. These are continuous Wilson lines in the case we have discussed it. So this actually fits the picture. And the message is this comes out. This was not put in, and we were very happy that it came out. The next question is now, given the fact that we know where the Higgs bosons are, where is the top quark? Now we have, in a certain way, made an assumption that we wanted to have a heavy top quark. So we looked for models where the top quark Yukawa does not necessarily vanish. So we actually considered that there is a Yukawa coupling which is of order unity in this picture. Once you do that, it actually turns out that, so that means the top has to have some kind of maximum overlap with the Higgs. And in fact, it turns out in these models that the top quark in the mini landscape, the top quark, lives in the untwisted sector as well. That's the message. And that also the top quark is not in a kind of localized, grand unified, complete multiplet. The top lives there, but the bottom can be somewhere else. So the third family is somewhat delocalized. They do not live together. The kids have left already the house, and they live in other places. So the top quark is in the untwisted sector, and the third family is distributed. Now what is interesting in the Z6-2, when we started to do it, we wanted complete SO10 families in 16. But it turned out 3 complete families we could not get. You can actually prove that that is impossible in the Z6-2 orbifold. So it was good that we did not succeed and that there's this theorem, because otherwise we wouldn't have gotten these nice models, because this is actually a very important ingredient for these models. So the Higgs live in the untwisted sector, and the top quark also lives in the untwisted sector. In certain tori in the untwisted sector, you have the left and the right top which live there. So now we have to start with the first and second family, and there's actually, this was found that in fact we can, they are localized. They come in 2 families, and they sit at this fixed point alpha equal to 1, beta equal to 1. One family lives at gamma equal to 1, and the other family lives at gamma equal to 3. So in some way you can see the last torus, that would be the torus which in some way Stewart was considering in his model before, if you would have considered such a model as the top-down version of his model. And in fact, it turns out that between these 2 fixed points, 1 and 3, in the third torus, you have a symmetry, and this is in fact here a D4 family symmetry. So we actually have a symmetry which could solve the flavor problem, the D4 symmetry, and we also understand why these two families, which are complete, they do not have this big Yukawa couplings as the top quark, because you see the Higgs, of course, is everywhere, but it's spread out. So if another field lives at a given point, it will not overlap so much with the Higgs, and that's why naturally these full families are supposed to be in twisted sectors, and they do not feel these additional symmetries which the fields might have that live in the untwisted sector. So we have, this is the picture, we have a heavy top, and actually we have this Yukawa unification because we have trilinear Yukawa coupling for the top. That's the string coupling, that coincides with the gauge coupling. Higgs doublets are in the untwisted sector, and the mu term is protected by a discrete symmetry. Now in these models of the mini landscape, this was a discrete symmetry of a rather high order. It was not the set for R, but I think that is something which you can, which appears here. The special thing about this symmetry, and that has also to do with these asymmetries as we understand now much better, as Michael has told us, is that the Higgs pair was neutral under all the symmetries, under all the selection rules of the orbifold. This means that if you would have allowed a mu term, then this mu term as a function of the fields would be allowed, multiplying h bar would be allowed in itself, because h bar is neutral under all the symmetries. So that means actually in this series where the mu term vanishes, also there is no constant term in the superpotential which is non-zero. And that means that you are actually starting from a Minkowski vacuum. And in that sense, that was the solution to the mu problem, which had already discussed by Casas and Munoz in 1993. The mu term is, in some way, it's not forbidden by supersymmetry, but in the particular supersymmetric vacuum you are starting with, it vanishes. And of course, we have the family symmetries for the other families. So these are the emergent localization problems. Repeating it, exactly 2 Higgs multiplets, not 24. We had 24 before, but when we got rid of all of them, 1 remained, even when we tried hard. So we couldn't get rid of it, and the reason was the symmetry. Only 1 trilinear Yukawa coupling, while there are models where also the tau can be in the untwisted sector, so you would have also a rather large coupling for the tau. So, and the fact that this top quark has the unique properties among the quarks and leptons has also important consequences for supersymmetry breakdown. That I want to discuss next, but I will cut that rather short because I want to get to some other point which I'll discuss later. You might remember that when you are doing a torus compactification, you have n equal to 4 supersymmetry, there were things appearing which are called no-scale models. These were models where you broke supersymmetry, the gravitino mass was non-zero, but all the soft masses vanished. Of course, the soft mass, the symmetry was not exact. When you did radiative corrections, you in some way could manage and break it, but the tree level was soft. So this is the no-scale property, and so we are expecting for the untwisted sector field a protection which is much stronger than a protection for the other fields. In fact, you see in the model with the SU4 hidden sector gauge group, in fact SU4 fits very nicely if you fit the gauge coupling constants at the gut scale and you compute the gravitino mass from gaugino condensation. Actually turns out that it is in the TeV, multi-TeV range. So what one gets in this picture is that you get a kind of mirage pattern for the soft masses. That means you have a compressed pattern of the gaugino masses. You have, let's say, normal quarks and leptons in the multi-TeV range. There is a parameter, log of m Planck over m3 half, which is a suppression, and that is the remnant of the n equal to 4 supersymmetry. So you have large gravitino mass, but you have suppressed soft terms for those fields which live in the untwisted sector, whereas you do not have suppressed soft terms for the fields that live in the twisted sectors. So the first two generations of quarks and leptons, they have masses of the order of the gravitino mass. The other parameters, the A parameters, the gaugino masses, and also the stops are in the TeV range, suppressed by this parameter log of m Planck over m3 half, which is a number of order 4 pi squared. And the mirage scheme comes from the fact that this now competes with radiative corrections, and that gives you a certain pattern. So this is what one gets, and this is something which I just wanted to show you here with a kind of benchmark model. So this is a model with a 4 TeV Cluino. You see here the lines which you see there are the contours of the mass of the lightest stop. So for example, at our benchmark points, we choose it to be rather light. The orange region is gone because of tachyons. The green region is ruled out by the Higgs mass constraints. The upper one, if you go in there, the Higgs mass would be too low, but you also see a green hatch here, and this one is where the Higgs mass actually is too large compared to what you get according to this one. So this will be the spectrum. We have a 4 TeV Cluino, we have heavy scalars, and we have the lightest Bino, and we have rather light stops. So this is a picture which appears in this thing. So the message is large gravitino, mirage pattern, suppressed stop masses. And these two things are severe challenges for LHC searches. Ben Allah has told you already, one of the reasons is when the stops are light. That's why it is called natural SUSY. But there's also this mirage pattern of the gaugino, which gives a compressed spectrum, which means when you produce the Cluino, it's not so much heavy compared to the lightest supersymmetric partners. So all these missing energy signals in a certain way get weakened. So, the overall scale. Now, there is no reliable prediction for the gravitino mass except for fine-tuning arguments. I remind you that some 30 years ago, when people discussed about colliders to some way clarify the weak scale, they had a no-lose theorem, and they said this machine should have 20 plus 20 TeV center of mass energy. So that's a bit more than the LHC has, and we have to worry whether the LHC satisfies this criterion. Let's hope it does. Well, we haven't seen anything at the LHC except for some hints for the Higgs mass. Let's suppose it is 125 GeV. Then we know this is rather high for the MSSM. It's not impossibly high, and it's rather low for the standard model. As you have seen before, in order to get the Higgs in this benchmark model, I had to, for example, go to a Cluino mass of 4 TeV. So this is rather high, and then you have to ask the question, where do we go? Will we be pushed out? And then on the other hand, we see that this Higgs mass is sufficiently high that it's not really killing the standard model. Yeah, in that sense, it is the standard model survives not really because in the standard model there is this limitation that when you run up the scale, then in some way you get the problem with this Yukawa self-coupling. It turns negative. That means instability. So you could argue that if this goes wrong at a certain scale, that's the place where new physics has to appear, even if there has nothing been before. So I'm now finishing the first part of my talk, and I'm now turning to some kind of nightmare scenario, which of course you might also think about. Let's suppose we are in the standard model, and then we have to see what are alternatives to SUSY. Now, one well-motivated physics beyond the standard model is axions. There are three what I call useful axions. This is the QCD axion. There's also axions have been used for natural supersymmetry and also as candidates for quintessence. So these are things which are useful. And of course, there is the whole axiverse, so there might be many more axions in string theory. They could be there, and one should look for them. In any case, you could now argue, well, if you push up the scale in the standard model, where's your dark matter candidate? Because you need some WIMP. that is one of the reasons for supersymmetry, but of course we know axions are a good dark matter candidate, so this is no longer an argument in such a scheme. Do axions need supersymmetry? Well, not necessarily. We know axion models typically don't need supersymmetry. Still, they can coexist, and there's nothing wrong with a supersymmetric axion model. As I said, strings, this has been discussed here already. Axions are abundant in string theory. The problem is that, well, of course they are abundant. In some cases, of course, you have to be careful, because when your way of fixing moduli fails and you give up at a certain point, a lot of axions might remain massless, and but maybe that was not because they are really, but because your mechanism failed. In any case, the axions which we take, they are massless in perturbation theory, and then they get masses by various non-perturbative effects, which then could give rise to various scales, depending whether you have inflation, you have a quintessential axion, you have a QCD axion. What is very generic in string theory is that the axion scales are of order of the string theory. So it's a challenge for every string theory to get an axion scale down to 10 to the 12 GeV, which would be the QCD axion scale. Yeah? Typically, this is very difficult, at least from the top-down approach. So this is something. So now you can ask the question, well, FA to be 10 to the 12 GeV seems to be sufficiently close to that value which we got when we are taking the standard model and running it up and waiting till lambda goes wrong. So we could now ask the question, well, maybe the axion scale also in string theory is so small because it is protected by some kind of supersymmetry. I do not mean it in the sense that supersymmetry forbids an axion scale. I mean it in the same sense as you can use arguments via supersymmetry to argue for a small mu term, although the mu term is not forbidden by supersymmetry. With the axion scale, this should be understood in the same way. So this 125 GeV is Haber high. So we could in some way think that there's new physics required at the intermediate scale. This has been put up by Hebecker, Knochen, and Weinberg a few months ago, and also I've seen in the last week there was a paper by Ibanez, Marquesano et al., which go along this several phase. It is actually, this lambda equal to 0 is a shift symmetry of the Kähler potential. It's a continuous Wilson line, so it actually fits the picture which we have. At that scale, in some way, we could have supersymmetry down to 10 to the 12 GeV, and we would have all the necessary things which we need in order to satisfy this. And again, this would be something which I would call a supersymmetry breaking at a large scale, which I'll call remote supersymmetry. So, of course, we have to understand the scales. We do not have any longer a fine-tuning argument for the weak scale. We need something else. We might have to use landscape arguments. And we then can discuss various fundamental mass scales in the theory. So the idea would be to get the axion scale in that theory as you get the mu scale in theories of low-scale supersymmetry with axions. So this would be a picture where these useful axions are in some way incorporated. There's an inflationary axion. In fact, there's one parameter which is the inflaton mass compared to the Planck mass, which gives you a factor of 10 to the 5. And with this factor of 10 to the 5, you can in some way explain all the other scales in a meaningful way. Of course, you would have to find for some of these an origin, and especially you would have to solve the hierarchy problem, because you can easily get a 3-level mass scale of the quintessential axion of 10 to the minus 33 electron volts, but of course it would in some way need some explanation why it is so small. So this brings me to the conclusions. I tried to explain to you that the localization of quarks, leptons, and Higgs bosons is very important, and that in some way, the realistic models we have constructed requires Higgs multiplets and top multiplets in the untwisted sector. And so this has to do with this solution of the mu problem. So I do not know any alternative of a solution to the mu problem in this series to this one. And in fact, this bottom-up argumentation, which Michael was doing from this question of the arc symmetries, it actually fits completely in that picture that this seems to be the way things work. So this implies gauge-Yukawa unification, which of course is consistent with the mass of the top quark. Our fields should be localized at fixed points. So they have family symmetries, they have smaller Yukawa couplings, this is immediately explained. And we have these remnants of n equal to 4 supersymmetry, which is a remnant of torus compactification, and it leads to this mass spectrum of kind of natural SUSY, which has been discussed. Second part has to do with the question of a situation that may be there is no weak scale supersymmetry, or weak scale supersymmetry is pushed up more and more. One nightmare alternative would be that's pushed up to something like 10 to the 12 GeV. It would be very difficult for us to check such a scenario, at least directly at colliders, or even, I think, dark matter. Of course, one could then really see whether dark matter, the axion, is the solution to that the axion is the solution to the dark matter. Even there, in some way, you see, there is this delocalized Higgs in the untwisted sector, which fits into that picture when supersymmetry would be pushed up to the 10 to the 12 GeV scale. Thank you very much.
Let's start with David.
Since the two light families are different places, do you run into trouble with the Cabibbo angle?
No. Well, no. You see, in this picture, when you work out these fields, there are various. There's a kind of Fogart-Nielsen mechanism where these fields couple to singlets, and that in some way is now a question of this Fogart-Nielsen mechanism to get the mass spectrum. We have checked in these models that in principle we can get masses to all quarks and leptons. Some masses come really at a Fogart-Nielsen scale where you have phi to the Fogart-Nielsen fields to the 5th power multiplying these fields. So typically at the trilinear level, these fields which are localized will be massless. You are right. Everything will vanish, but of course there is this Fogart-Nielsen mechanism which explains the small masses and also the angles.
I think Stuart was next.
Yeah, so I don't understand remote supersymmetry. Is that the same as split supersymmetry?
Well, if you take it serious, well, you see, if you would take it as a supersymmetric scenario, it would mean in the generic way, it would mean that it's not split supersymmetry, but the gauginos are also around that scale. Maybe a factor 1 or 2 small. But now you, of course, in some way, you have to ask the question, what do I do? How do I solve the naturalness problem? Now, depending on what you are doing there, you might, it's completely open. You might get split supersymmetry, or you name it what supersymmetry, or whatever.
Okay, question.
I have 2 questions. One is also related to the previous talk. When you analyze the supersymmetry breaking, the first part of the talk, of course, did you take into account the constraints from the Z4 symmetry for the fields that could get, that could break supersymmetry, the F term of the which fields should have?
No, this model has no Z4 symmetry. This is it's actually a symmetry. It's a discrete symmetry which up to order 8 of terms in the superpotential was exact. So it was in a certain way 0, and then it turned out that at order 9 or so in the superpotential you actually got a mu term.
So that was accidental then?
Yeah, but we could then see that it was actually a discrete R symmetry, which was the underlying symmetry. It was not the set for R.
was
But you see, in this model, we have not discussed these questions that we want to allow this operator or that operator. So this was just the symmetry which we found. Now there might be better there might be better symmetries like the set for R, but you see, my attitude is more in the string theories, these discrete symmetries are abundant. Yeah?
No, I understand, but if there is some reason, some discrete symmetry, whether it's
Yeah.
A4 or something else, it's to be seen,
Yeah.
that protects the middle level, then you would like to preserve this discrete symmetry when you break supersymmetry. In other words,
No,
the
you
fields
cannot,
that could
you
get
cannot.
less.
No, you cannot. I mean, the thing is, you have to switch superpotential vacuum excitation value for the cosmological constant, and this breaks any R symmetry. The remaining symmetry is just matter parity or C2.
But then
No, the
in
point-
what
the
sense-
point
in
is
what
the point-
sense then,
yes, you
if
see-
break this asymmetry, then in what sense you can protect?
No, just wait a moment. What I told you is that this symmetry not only protects the mean term, but it protects any term in the superpotential, which is built out of fields which could give you the mu term. Yeah? Now, when you break supersymmetry, you know that the vacuum expectation value of the superpotential will be m3/2. So once you break supersymmetry, that would mean the mu term becomes out of order m3/2. You cannot compute it from first principle, but it will be of order m3/2. Because in the limits that the vacuum expectation value of the superpotential vanishes, which is the supersymmetric limit, the mu term will vanish. Now, of course, there could be a numerical factor, but
But in that case, this expectation value will come from the non-perturbative effect
Yeah.
to the minus.
Yeah.
Either
some.
non-perturbative effects or perturbative effects.
Perturbative.
In his case, it was perturbative effects, higher order terms in the
It
superpotential.
just appeared at very, very high order.
And the second question is, what is wrong with the Giudice-Massiel mechanism in these models?
Like,
Nothing.
So that's an alternative.
Yes, but you don't need it.
no, but you see, the question here is not, it's not to get a mu term, it's to forbid the mu term. You see, you have hundreds of
Yeah,
Higgs
okay.
doublets pairs, and you have to get rid of them, and whenever you try to do it, in some models, you get rid of them all. So generically, in string theory, the mu term is of order of the string scale. So now here, when we try to get rid of it, we actually were not successful.
However, you can take.
There are other ways of making this model wrong. That I agree. You can have
No, what I'm saying is that you can, in your model, you can check whether in the Keller potential there are corrections
Yeah.
which
Yeah.
can give rise to Giudice-Massiel, in other words, corrections of the order.
But as I told you, this scalar potential will be very much protected because there are these shift symmetries, yeah, which in a certain way are remnants. So this scalar potential actually is the usual scalar potential which you will get when you do torus compactification, at least for that purpose.
Okay, Fernando?
It's usable.
For the supersymmetry breaking, you have the Gaussian condensation.
I didn't hear you.
Yes.
So
You can discuss this over coffee.
my voice is
because
not
we don't
your,
hear-
your whispering is stronger than my point. So for supersymmetry breaking, you break it by Gaussian condensation. So
Yeah.
who is the F term of which field is the dominant part for supersymmetry breaking?
Well, the F term, I have given talks on that, where half of the talk was consisting of this. So the point is here that you fix all moduli and you will remain with the dilaton, yeah, which is the big problem. Now, you have a runaway dilaton. And now, of course, with the runaway dilaton, you know you can do some non-perturbative effects in the Kähler potential and you stabilize it. The problem, however, is when you do that, you get a positive cosmological constant which is too big. So then you actually have to downlift it. Yeah, so this is what we are doing. We are doing what KKLT do in type 2D. We do here as a downlift in the heterodic one. And actually when we do that, we actually can see that we can fix the dilaton in this minimum with the other field, yeah, with superpotential. And then we can forget about these non-perturbative terms which were used. So it actually slides down to minimum, it's fixed, and it is actually this field which is responsible for the adjustment of the cosmological constant, which has the large supersymmetry break. And the dilaton is suppressed by this factor log of m Planck over m3 half. So you see the dilaton is subleading, and that gives you this mirage picture, because this means the gaugino masses, for example, will be smaller than the other ones, because they will only feel the contribution from the dilaton.
But then this field is twisted or untwisted?
This is an untwisted field.
So then, for your soft terms, is there a difference between the S top and the other families? Because in the same way that the top was untwisted and was heavier because it was in the untwisted sector, is there a different pattern in the soft?
Well, typically you would expect in such a situation, and that's the reason why I make this argument really about this enhanced supersymmetry in the twisted sector. So what sits in the untwisted sector gets suppressed supersymmetry. So the stops are lighter than the others, because they sit in the untwisted sector. That's natural supersymmetry. That's the twist in this model, which in some way comes out if you stare long enough at it.
Okay, any more really urgent questions? Then let's thank Hans Peter again.